So the topic for me will be powering data centers and optimizing system efficiency through utilization of waste heat. And I think this topic fits quite well into this year's topic of the Xcelerate, that is human plus machine powering every decision, because I think data centers are the backbone of this energy transition that we all see, and the power surge is huge. And I think we should not only look at the power side, but also look at the efficiency and the sustainability. And that's why I have a Plexus model here that combines the data center with the heat pump and using the waste heat. Let me guide you through the agenda that I have. First, I want to give you a few overview of Everllence. Some of you may already be familiar with us under another name. Then I jump into the data center system concept, talking about some key metrics first, some challenges, and show you the Plexus model. And in the end, I will get over some simulation results and give you some key takeaways. So who is Everllence? We are formerly MAN Energy Solutions, and I brought some years here. So I think we can all agree that 2015 and the Paris Agreement is a huge step in history for us to model. And we built up in 2018 and made decarbonization to our main target in our business activities. And last year, 2025, we rebranded into Everllence. And let me give you a few words about Everllence, maybe that you can better remember the name. So it comes from two parts. It's first ever. That's because we have a huge history for more than over 2 centuries, coming with the first ever diesel engine in Augsburg. And we, for example, had the first subsea compressor. We have the biggest river heat pump in Europe that we're building right now. And that's the first part, and the second part is excellence, and we think we make our products with excellence, and therefore we came to that name. That are our products. So the main topic is really decarbonization, and I think in the middle is, on the one hand, our large-scale heat pumps, where we are able to use electricity to generate heat from carbon-neutral electricity in that sense. We're having future-fuel engines. They can run on a variety of climate-neutral fuels, let it be SNG, let it be methanol, ammonia, or other fuels in the future. Then retrofits is a big pillar that we are trying to implement because our vessels or power plant engines run for a very long time, and therefore it's important that we replace them sometime to make them run on future fuels. And the last pillar is CCS, CCUS, so carbon capture, utilization, and storage. So that closes the loop within decarbonization and being able to tackle the challenges in hard-to-abate sectors. But let me speak about the topic itself, data center system concept. And let me start with some key metrics that are very important. And I brought 4 key metrics that especially in Europe, are important, but I think for all data center projects, these abbreviations are top priority, and especially the PUE, that is the power usage effectiveness, where the IT power consumption is in relation to the power consumption of the whole data center. And Germany, for example, from 2027, next year, from next year on, there's the obligation to be below 1.2. So that's a key metric that we have to tackle in data center projects. Then we have the renewable energy factor that counts how much renewable energy is used powering a data center. We've got the water usage effectiveness, so how much water is used per IT load. And the last abbreviation is ERF, so energy reuse factor, that I want to tackle in this presentation, especially how much energy that I put into the data center is then reused, for example, in a district heating energy system or in industries or wherever it's possible. And there are many challenges when we speak about data center development. So this is just a slide to give you an overview of what is possible, but there are so many more challenges, starting with the PUE. So the engineering guys have to work much to achieve those low PUEs. We have cooling infrastructure, so it's important to look where the location of the data center is. Do I have water available? How can I cool my data center? Do I have high temperatures? Is it on high altitudes? Where can I reuse my heat? If it's an obligation in the legislation, for example, there are geographical risks, for example, natural disasters, earthquakes, floods, hurricanes. I have the challenge of power availability and the reliability. Oftentimes, the network connection is not yet ready for such huge data centers or just stepwise, so that I need to account for. I need green energy integration as we want to decarbonize, and especially for data centers, the network connectivity is a huge challenge. As an example, being in Frankfurt am Main in Germany, where it's famous because of the good network connection, but there the network connection is not available in the next few years for most of the data centers. So let me now go into the model input data. So I just want to guide you through what I did. The model is quite simple to be able to present it in a really short time. And as you just saw, there are many challenges and complexity rises with time in the real projects. So first, I have the IT load distribution, which has a huge influence on the project, especially as the IT load distribution sets how much heat do I have after the data center use the electricity. And here I've got a AI data center with the electrical peak capacity. That's one of the key parameters. Let it be 100 megawatts in this case, and the waste heat corresponds to this capacity. Then if we look at the power supply, here I used an engine because we make engines. You can have a natural gas price there or be SNG gas price. We need to account for the high flexibility that is needed, and we need to model also the fast start capabilities of those power plants, and if we have derating or high altitudes, as I just said. And the third thing is that we want to look at the heat and the cold supply. In this case, I want to achieve a constant heat and cold supply for the district heat energy system. That's why we use a heat storage between the heat pump and the district heat system. It's also important to look at the cold and hot COP of the heat pump, so how efficient does it produce heat and also cold. Especially the temperatures are here influential. That depends from data center to data center, which cooling temperature is needed, what's the waste heat temperature that I have. And I brought some pictures here that you're not only seeing charts and numbers, but also some of our technologies. Here's the engine type I used in the model. It's around 20 megawatts, and there's a smaller engine and some compressor types that I use in our heat pumps to different models. Then let me dive into the technical concept. Here you can have a power grid, as I just said, or use the engine power plant that is powering the data center and the heat pump. We've got the excess heat that goes from the data center into the heat pump. We've got a cooling stream going back to the data center. We've got a heating stream that goes either into the heat storage or directly into the district heat energy system. And it's a very simplified system, but it works quite well with the temperatures that we have here. And I brought a little outlook because oftentimes, for example, if you need lower temperatures, you would use an absorption chiller. If you would use the excess heat of your power plant, let it be the engine power plant, you could use it as well in the absorption chiller. You could use air coolers that are way cheaper or have some spare ones. So that's all possible. And next slide, I want to show you how I modeled it in Plexos. So here you can find the icons that you know from Plexos. So we've got the natural gas going into the engine. We've got a power node here and a district heat node there. And maybe you wonder why the data center is in power to X. I mean, what it does is it takes electricity and I get heat out of it. And You may also notice that there's no connection between the cooling node and the data center. That is because I used the data file that is the IT load from the data center using a variable, so it's connected, and the cooling demand is in this node. Then additionally, I've got the heat storage in the Plexus model and a spare heat market if there's any excess, so all my constraints are working just fine. I've got some fixed cooling to heating ratios of the heat pump, so this does not change within the model. And the heat storage allows that I get as an output a constant heat load from a district heat system. You could also just use all the heat that is available from the data center into the heat pump and then use it as it comes. I think it depends what my sink is working with. So then jump directly into the simulation results and give you some key takeaways. So here again you see the data center load. It's a distribution that averages with 70%. I need to say this is one example. It depends from project to project how your IT load distribution looks like. This could be an AI interference IT load, but there are so many alternatives like storage, which is maybe more like base load, or some AI training that has different capacity levels that I need to tackle. And this makes, out of this, the heat supplied by the heat pump arises. In this section, I've got a constant heat load, and everything above is my excess heat that I either am able to use or need to cool away. And a good thing is that the heat pumps raise the heat that comes out of the data center, which is maybe 30, 40, in this case 40 degrees Celsius, and I'm able to bring it up to, let's say 88 in this case, but it can also be a higher temperature that I can use in a district heat energy system. Also, the heat consumption can be seasonally, so this makes the business case interesting. How much heat can I get rid of in the summer, or can I use in the winter? And in the last chart, you see the heat storage working, and this heat storage makes it possible that we have this constant load. You could also make the heat storage bigger and then have less excess heat. I think it's an optimizing problem, and also you need to get the financial numbers into there, whether it makes sense to spend more money for bigger heat storage. Then I go to the takeaways. Why does it make sense to have a heat pump within a data center system and have this heat recovery option? So first, you need to comply to laws, and especially in Germany, you need to use at least 10 or 20% of the waste heat. Then you've got additional value streams. If you are able to sell the heat, you can achieve the low POE that reduces your electricity cost. If it's the case that you have a CO2 reduction in the heat system through the waste recovery, in case you have a gas boiler that you are replacing, that's always good. And you've got automatically noise reduction through the use of a heat pump. And I also want to give you two catching words at the end of the presentation. One is adaptation. So the solution must align with each site's unique operating conditions. So this is a simple case, but it really fast gets very complicated, and it must fit to the data center that I'm having as project in front of me. And the retrofit, because I think it's also important as data centers get better and better every year, and especially the chips, you need to think about whether you can retrofit the data center and use the waste heat, not now, but in 2 or 3 years, if it's possible. So thank you. I made it short, so you have some spare time before the event is going on. I'm looking forward to see you there, and I'm ready for some questions if there are one.
Yeah, thanks for that case study. Maybe a comment and then a question. I was going to comment on the slide about challenges to data center development.
Sure, I can go back quickly.
Did not include kind of public or social acceptance or community buy-in. I think in the United States right now, we're starting to see more public pushback or concern about data center development as they're reaching really more significantly at a larger scale. But then second, a question, I may have missed it, but what kind of heat storage technologies are you using? I saw the generator, the heat pump, the compressor, but what are you considering here for heat storage for the technology?
So great question, thank you. Yeah, I think it's very important to look at the challenges, and especially the residential areas have their opinion on those data centers nearby. And I think there are many, many more challenges that I need to address, where the slide is not big enough. So thank you for your comment. For the heat storage, it really depends on what I want to do and what my heat sink is. In this case, I use water storage, just hot water storage, as it's quite usual to store the heat for, I think in this model, 10 hours at a temperature of around 90 degrees.
Any more questions?
Yep, thank you. Thank you for the presentation. Maybe related to the acceptability, to what extent do you see these opportunities being applicable for hyperscalers, like 1 gigawatt data centers?
Great question, thank you. I think it's applicable for like every data center. I think the biggest challenge is, in this case, to find any heatsink that is available. And if the IT load let's be 1 gigawatt, then I think you've got enough excess heat to make it somehow possible to use it. And I think you should. So every project should at least take a look whether it's possible and do it. I think that's the case.
Hi, Ali here from ESB. I have a quick question for you. Can you go to the slide that you showed the IT load, please?
Sure. This one?
Yeah, at least in Ireland, we usually model the data centers as base load component of the demand. So what do you think if you combine a fleet of data centers, how that IT load might look like if you combine a bunch of data centers?
So very good question. That's what we also looked at. This one is one example for an, as I just said, AI data center with interference. So that's the case for many data centers like co-locators. And I think at least for the waste heat recovery, it gets better and better if more IT load is laid over another. So it's getting like more constant or more in the direction of base load. And I think that's always good. So. All right, if there are any more questions, I'm happy to answer them within the conference. I'm here until Friday. I'm happy if someone approaches me. Otherwise, I hope to see you at the evening event today. And thank you very much for your attention.